My name is Steve Kokelj, and I'm the permafrost scientist with the Northwest Territories Geological Survey. This presentation, titled The Thermokarst Environments of Northwestern Canada, summarizes the results of a unique opportunity to systematically inventory the thermokarst landforms across Northwest Territories through an aerial survey campaign in summer of 2020. For our team, it was a bright light in a very difficult period for all of us due to COVID-19. This work was possible due to an alignment of circumstances facilitated by the hard work of a number of individuals, collaborators, and funders committed to Northern science. I would like to acknowledge my co-authors, several of which are Northern-based scientists, and without their skills, this program would not have been possible. We also acknowledge Peter Morris and Steve Wolf of the Geological Survey of Canada and Trevor Lance of UVic, who provided their undivided attention on some key scientific issues that ensured successful data collection. We are indebted to the Government of the Northwest Territories, notably Public Health, which developed policies and procedures enabling safe travel within the Northwest Territories, and the support of the Northwest Territories Geological Survey. We also thank the Polar Continental Shelf Program, who provided aircraft support and logistical coordination to conduct a 13,000-kilometer aerial survey of thermokarst terrain in the Northwest Territories. Despite the challenges due to COVID-19, we were able to conduct this work safely and efficiently, thanks to our air charter companies, their pilots, and crews. Permafrost thaw and the issue of northern landscape change is one of the hottest topics in Arctic science because of its linkages to the carbon-climate feedback, impacts on terrestrial and aquatic ecosystems, and on northern communities and critical infrastructure. The challenge of understanding permafrost thaw has led to the production of continental to circumpolar scale maps of sensitive permafrost terrain. Their development has been facilitated by increasing capacity in geoprocessing, remote sensing, and modeling. However, linking these outputs to empirical reality remains a critical step towards informed climate change adaptation, northern decision-making, and to better understand what permafrost thaw really means to the landscapes and to the people of the North. The critical gap between linking broad-scale outputs to regional or local-scale knowledge has prompted the development of a grassroots thermokarst mapping collaborative with the goals of developing Northwest Territory-wide mapping products characterizing the thaw sensitivity of permafrost terrain. Collaboratively, developing these products fosters knowledge sharing and building relationships between scientists, northerners, and decision makers. Tristan Gingrahill is providing a project summary presentation, so I only provide a brief overview of the project here. This project has adopted a mapping framework that implements a 7.5 by 7.5 kilometer grid system. Theme experts developed mapping rubrics for the main themes of mass wasting, hydrological, paraglacial, and organic terrain features. Mappers implement a rubric supported by a geodatabase to classify grid cells by inspecting sentinel and high-resolution spot imagery. The aim is to rapidly identify whether grid cells are affected by particular thermokarst processes or sensitive landscape features. The mapping has progressed well and has provided opportunities to train several young scientists and community members in identification of features indicating permafrost landscape change. The panel on the left shows mapping progress for the mass wasting theme, where over 40% of the mapping has been completed. Validating the mapping product is a project objective, and several procedures including QA/QC on data quality through geoprocessing, comparison with existing mapping products, and mapper-to-mapper comparison are all being conducted. Perhaps the most exciting is to develop complementary products which enable linking broad-scale mapping to ground-based knowledge of thermokarst and paraglacial processes. Development of intermediate-scale validation through observationally based aerial surveys is a topic of the remainder of this presentation. In summer 2020, several factors conspired to enable this project. By midsummer, travel within the Northwest Territories for Northern residents was possible, concurrent with PCSP support for some Northern-led projects, opening the door for our work. Three other critical factors were also in place. There was an existing geodatabase for characterizing thermokarst terrain types, built and refined for thermokarst mapping for the thermokarst mapping project. Secondly, Our northern-based team members were already developing permafrost survey templates using Esri's Survey 123 app, and they were immediately able to link the Geodatabase with the app to facilitate collection and organization of aerial survey information. Thirdly, there is finally a growing northern-based scientific capacity to implement or even lead permafrost and environmental geoscience projects in the Northwest Territories. Being able to capitalize on the opportunity in 2020 highlights the clear need for northern-based science capacity to advance field programs, leverage collaborative relationships, and link scientific initiatives to northern needs. The team quickly adopted, enhanced, and modified the Thermokarst mapping geodatabase such that observations and characteristics of complex landforms could be rapidly recorded as an expert interpreter described features, and a third team member obtained georeference photographs. Implementation of the protocol was iterative, requiring some adjustments to secure robust records of aerial observations. The process of data collection also served as active training in permafrost geomorphology for all team members. This slide shows the data model as structured to accommodate the Survey 123 platform. Here, the team was viewing a deep-seated landslide. It was located in a mixed forest ecological setting in a fluvially incised and colluvial landscape. The feature is a translational failure that is bedrock controlled and characterized by block or slab that has remained intact. Closer inspection confirmed a failure plane in poorly indurated shale bedrock. The disturbance is recent and it meets the size criteria to be classified as a mega disturbance. Photographs and descriptions refer to a single feature, a headscarp height exceeds 5 meters, and the connectivity to the downstream system, which is fluvial, is indicated by a 1 where there's contact between colluvial and the downstream environment. Ground ice was not observed in the exposure. For contrast, the second example for thawing slopes and mass wasting is a large retrogressive thaw slump. Assessment information modified from the previous example are highlighted in blue. The large slump is located in ice-rich, fluvially incised moraine in a tundra environment. The disturbance is dynamic and complex, where rapid growth of this large disturbance has cannibalized older or smaller thaw slumps on the valley sides that are being consumed by this impressive mass wasting feature. The head walls exceed 20 meters height and reveal relic massive ice tens of meters thickness that underlies this glaciated landscape. Translocation of thawed materials by fluidized flow have traveled well over a kilometer down valley, indicating a connectivity class of 2. This data shows the model for a thermokarst or thaw lake feature occurring in mixed forest and wetland setting that was recently burned. The physiography is bedrock and lacustrine. The feature characteristics are shoreline collapse and lake expansion. Terraces in the ponds suggest possible lowering of lake level, and these characteristics are coupled with rims near shorelines that are diagnostic of a classic Ramparted lake lithalsa complex, which develops in ice-rich deposits and comprises thaw-sensitive terrain. The site has both lakes and ponds, and the final field indicates a moderate spatial extent of the landscape that is affected by the processes described above. In this slide, we show an organic deposit in a lowland basin near the treeline in the North Slave region. Surrounding terrain is bedrock-dominated shield, and lowland areas of lacustrine materials typically host organic deposits or peatlands. This feature in the transitional zone is characterized by one of the most southerly observations of polygonal terrain in this region, adjacent to a string bog and a pattern forest. Drainage is rectangular in association with the ice wedges, and multi-basinal associated with pattern ponding in the polygonal and string bog settings. Degradation of the peatland is low, and the area constitutes a medium-sized basin, reflecting heterogeneity in this mosaic landscape. In summer 2020, the Thermokarst inventory covered the southern Arctic, tundra, taiga cordillera, taiga plains, and taiga shield areas and assessed over 13,500 kilometers of flight line, compiling over 3,000 observations and over 19,000 georeferenced photos organized in a geospatial database. The data model evolved over the first few surveys, requiring some adaptation. Integration of advances in geomatics and web technology with well thought through data models enabled the raw data collected this summer to be compiled and visualized in the preliminary summaries. The last few slides provide some very basic examples of these outputs and the utility of the data. This slide shows an example of flight lines in the Beaufort Delta region underlain by grid cells classified according to the presence of 1, 2, or 3 types of major mass wasting. The white grid cells were mapped, but many are in the Mackenzie Delta alluvium, and as we can see, mass wasting is not dominant there. The western margins of the delta are fluvially incised ice-rich moraines. The diamonds show observations of retrogressive thaw slumps, shallow and deep slides. Simple summary shows that 100% of the thaw slumps observed in the aerial summaries are in grid cells classified accordingly, and 83% of the deep slides and 70% of the shallow slides. Major slides on the eastern margins of the Richardson Mountains were observed while flying over the delta, so the helicopter position becomes disconnected from the exact location of the phenomenon, and this is reconciled through the QA/QC process, which is occurring now. Secondly, as climate warms and precipitation intensifies, shallow slides in the region increasingly evolve into retrogressive thaw slumps, or may be sufficiently small that they're difficult to recognize on the sentinel imagery, or the date of the imagery, in fact, predates their occurrence. So this contributes to the poorer mapping performance for shallow slides. The white data points are oblique photographs from an ecosystem land classification data set developed by the NWT, and these photos will be reassessed and integrated into our database. The map on the left shows grid cells identifying the presence and abundance of Ramparted Lake lithalsa complexes in the Yellowknife region, and the crosses indicate our aerial inventory of these features. Mapping did a good job capturing the distribution of this landform with few aerial observations in unclassified grid cells. While the primary use of the data was viewed to support QA/QC of the grid-based mapping, the data also provides the potential to explore statistical associations between thermokarst terrain types and controls on their distribution. In this simple example, we plot the proportion of ice wedge observations with respect to distance from treeline. The data illustrates the basic broad-scale control of climate and ecology on thermal contraction cracking and ice wedge distribution. The elevated spike in the lower end of the chart reflects the presence of polygonal terrain in the Horn Plateau uplands of the south-central taiga plains. Other information extracted from our data shows the relative proportion of slope failure modes across our survey domain, extending from Arctic tundra to boreal forest. The data suggests that mechanisms of top-down thaw, including retrogressive thaw slumps and active layer slides, are dominant in cold continuous permafrost. However, the importance of deep-seated failures, which occur due to a loss of soil strength at depth, are increasingly predominant in southern regions where the permafrost is warm and thin and may be thawing at its base. In summary, geomatics technology, a thermokarst data model, northern science capacity, and polar continental shelf support made possible a broad-scale systematic inventory of thermokarst landforms in the Northwest Territories. Outputs from this project will support mapper training and map validation. There's potential to use this data to explore controls on the distribution of thermokarst or sensitive permafrost terrain. Northerners can also be directly involved in inventorying thermokarst and permafrost landscapes using these tools. And finally, broader adaptation of methods can rapidly enhance an observational thermokarst database for Northern Canada. Thank you for listening, and I hope you enjoyed this talk.